In this video, we're going to discuss autonomous equations. An ordinary differential equation in which the independent variable t does not appear explicitly is said to be autonomous. In other words, an autonomous ODE has the form dx dt equal to f of x. In our previous discussions, we've talked about dx dt equal to some f of t and x. But here again, that t value does not appear explicitly. So we just have the function dx dt equal to f of, and then our function is of the dependent variable x here. And again, that is called an autonomous first order ordinary differential equation. These turn out to be to show up in the real world quite often. So there's a reason that we actually want to look at this and spend the time taking a look at this. And it turns out that if we have something of this form, we can quickly sketch out what all of the possible solutions will be given some initial value. And in fact, really, we don't even need to know what the initial value is, but we can sketch out what the solution will look like, no matter what the initial value is. In particular, we do a lot of our work around what we call the equilibrium solutions. Well, if c is a root of this function f of x, then the constant function x equals c is a solution to this autonomous equation. We can note that if c is a root of the function f of x, that means if we plug in x equals c on the right, we do get 0. That's what it means to be a root of that function. And then if we have the x equals c as our constant function and we take the derivative of that, the derivative of a constant function is 0. So we get 0 on the left as well. And therefore we see that that is in fact a solution. And again, we call that an equilibrium solution because if we have a solution at that particular x value, then the solution stays at that x value no matter what t does, as t ranges through everything. So we call that an equilibrium solution because the solution stays there. All right. We're going to end up restricting our attention to just autonomous equations with f and partial f with respect to x being continuous everywhere. And if that is the case, then that means the existence and uniqueness theorem is satisfied for every initial value. What that means is the uniqueness part of this guarantees that distinct solutions, those curves, cannot intersect in the tx plane. In other words, if we have the tx plane here, and we have some equilibrium solution, no non-equilibrium solution can end up crossing that equilibrium solution at any point. If they did cross at any point, then the uniqueness part of the existence and uniqueness theorem would not be satisfied at that given point, because if that happened to be our initial value, then we would have two solutions here, so the uniqueness part would not be satisfied. But since we know that the uniqueness part must be satisfied everywhere, then for every initial value, then we know that this cannot happen, that we cannot have two solutions cross each other. And that's not true for just non-equilibrium solutions and equilibrium solutions. Any two non-equilibrium solutions cannot cross each other either. Another way to put that is that if any two solutions do have an intersecting point, it turns out they're the same solution, so they actually intersect everywhere. All right. Moreover, we go ahead and label these equilibrium solutions as either stable, unstable, or semi-stable based on the behavior of the surrounding non-equilibrium solutions. So we see in this first picture, our equilibrium solutions there in the middle. And if the non-equilibrium solutions on either side of that approach the equilibrium solution, then we say the equilibrium solution is stable And why is that? Why that terminology? Well, all solutions near that point kind of converge towards that equilibrium point. So the system is said to be stable there, or the equilibrium solution is said to be stable near that point. However, in this next picture, if the non-equilibrium solutions move away from the equilibrium solution, then our equilibrium solution is said to be unstable. So any perturbation of the solution away from the equilibrium solution then forces the solution to, or the system to move away from that equilibrium solution. So that is called unstable because the system is unstable there. If we get a picture like either of these two last ones, where one side approaches the equilibrium solution and the other side moves away from it, then the equilibrium solution is said to be semi-stable in that situation. So what we're going to do is we're going to look at autonomous equations here. We're going to find their equilibrium solutions, and then we're going to determine the intervals of x that the non-equilibrium solutions increase or decrease, and use that to sketch. We're going to kind of do part 2 and 3 here at the same time. And then after we do all of that, we should easily be able to classify each equilibrium solution as either stable, unstable, or semi-stable. And what this will ultimately do is give us a picture that shows us all types of solutions to the autonomous first order ordinary differential equation. And we'll do that in the next video here.